Hi everyone, welcome to another set of videos. This is another topic under graph theory, another set of path and circuit. We have what we call Hamiltonian path and circuit. Then we will discuss also other topics like weighted graph and planar graph. The application of this Hamiltonian circuit is actually the traveling salesman problem. So what is this all about? Given a set of cities and distance between every pair of cities, the problem is to find the shortest possible route that visits every city exactly once. And you may also return to the starting point. One good application of the TSP or the traveling salesman problem is actually the optimal tour of Sweden. In May 2004, the traveling salesman problem of visiting all 24,978 cities in Sweden was solved. A tour of length of approximately 72,500 kilometers was found, and it was proven that no shorter tour exists. At the time of the computation, this was the largest solved TSP instance, surpassing the previous record of 15,112 cities through Germany set in April 2001. So let's define the basic term, a Hamiltonian path and circuit. A Hamiltonian path of a graph is a path passing through its vertex of the graph exactly once. If the path is closed, it is called a Hamiltonian cycle or circuit. And if a graph has a Hamiltonian cycle, it is called Hamiltonian. So if you can still recall the difference of this with that of Euler path or Euler circuit, what we consider in the Euler path or circuit is the edges that we're going to just pass through the edges exactly once. While for Hamiltonian, it should be the vertices that you should pass through exactly once. Okay, so you need to pass through the vertices exactly once. Let's say, for example, let's determine a Hamiltonian path here. So we need to pass through all the cities. So if these are cities, okay, I think these are cities in the United States of America. So for a Hamiltonian path, we need to pass through all the cities exactly once. And you can take any route or any edges here or lines as long as you will pass through from all the cities. So you may start with Portland, you take this route here or edge, you go to Boise, you go to Booth, and then next Salt Lake City, to Reno, to Sacramento, and to go back to Portland. When you go back to Portland, that becomes a circuit. Okay, you stop at Sacramento and you already pass through all these cities here. That's only a Hamiltonian path. Okay, and you should actually just pass through these cities exactly once. Okay, so that's the difference of the Hamiltonian with that of the Euler. Now, how to determine, okay, whether a graph is actually a Hamiltonian or not? We have here a theorem, the Dirac's theorem. Consider a connected graph with at least 3 vertices and no multiple edges. Let n be the number of vertices in the graph. If every vertex has a degree of at least n over 2, then the graph must be Hamiltonian. But you have to remember, if the hypothesis of Dirac's theorem is not satisfied, it does not mean that the graph is not Hamiltonian. Okay, so even the graph does not satisfy the Dirac's theorem, we can still, or there's are actually graphs which are Hamiltonian even if it will not follow or satisfy the Dirac theorem. But what is the point here of Dirac is, for every graph that will satisfy this theorem, it is actually Hamiltonian. But it doesn't mean that if a graph does not satisfy his theorem or this theorem, we cannot conclude that it's not Hamiltonian. Okay, let's have an example. So in here, if we're going to count the number of vertices, there are 1, 2, 3, 4, 5, 6. So if you're going to divide, okay, that 6 into 2, that gives you 3. Therefore, from Dirac's theorem, the degree of its vertices or its vertex should be at least 3, greater than or equal to this, which is 3. So if we're going to actually look into the degree of these vertices here, the degree here is 3, the degree here is 4, the degree of this is 3, the degree is 4 here, the degree of this one is 5, and the degree of this is 3. So as you can see, all the degrees are greater than or equal to 3. Therefore, we can conclude that in this graph there is a Hamiltonian path or circuit. And then you can actually have that starting from Portland, you go to Boise, to Butte, to Salt Lake City, to Reno, Sacramento, and you go back to Portland. So therefore, there is a Hamiltonian circuit. In this example, or another graph here, if we're going to apply the Dirac's theorem, we need to count the number of vertices. We have 1, 2, 3, 4, 5, 6, 7. So 7 over 2, that gives you 3.5. Okay, so that's the meaning of the Dirac's theorem, and it means that the degree of its vertices should be greater than or equal to 3. But checking now the degree of its vertices here, start with Los Angeles, for example, the degree is 3. In here, the degree is 4. The degree here is 3. The degree here is 3 also. Here we have 3. And then here 3. And then here 3. I'm sorry, this should be 3.5, no? Because this one, the one that we solve here, that was solved is actually 3.5. So Dirac's theorem tells us that its vertex should have actually a degree greater than or equal to 3.5, so that we can immediately conclude it's actually a Hamiltonian circuit. But as you can see, there are actually degrees which are less than 3.5. Okay, so we cannot say that there is actually a Hamiltonian path, or maybe there is no Hamiltonian path or circuit. Okay, so from this theorem, this theorem tells us that if it satisfies the Dirac theorem, if this one it's greater than 3.5, automatically there is a Hamiltonian, okay, circuit. But it doesn't mean also that if it does not satisfy the Dirac, there will be no more Hamiltonian. There is still, okay, in some graphs. So let's check whether there's still a Hamiltonian path here, even it does not actually satisfy the Dirac's theorem. And you can see actually that there is. If you start with Los Angeles, you can actually go to San Francisco. Okay. I'm sorry. You may actually go to okay, you may actually go to San Francisco, and then to Boston, then to New York, okay, and then to Atlanta, Dallas, to Phoenix, and then you go back to Los Angeles. Therefore, there is actually a Hamiltonian circuit. Okay, so it did not actually repeat any of the vertices here. Okay, now the next term is what we call weighted graph. So a weighted graph is a graph in which its edge is associated with a value called a weight. So this is an example of a weighted graph. So with these numbers here, which maybe corresponds to the distance, okay, between the cities. So this number can be actually the distance, or it can be also the time used in traveling from one city to another, or it may actually represent also the cost of transportation from one city to another city. So that's why that's the weight. Okay, so the weight may refer to a distance, it may refer to a time, or to a cost or a money. Okay, and then we have here an example of an application of weighted graph. So the table below lists the distances in miles between 6 popular cities that a particular airline fly to. Suppose a traveler would like to start in Chicago, visit the other 5 cities this airline flies to, and return to Chicago. Find 3 different routes that the traveler could follow, and find the distance flown for each route. Okay, so you need to, for every destination, you need to actually make a point or a vertex for these cities that corresponds to vertices. And the weight here, it means that there are actually a travel, okay, a travel or transportation from that city to another city. If there's no flight, meaning you cannot connect, there's no connection between the two cities here. So you can actually convert that table into a graph. So let's say, for example, let's take Chicago connected to New York. So that's 713. Chicago to Washington, 597. So this is the line, 597. 665, that's from Chicago to Philadelphia. So we have Chicago to Philadelphia here, and then we have Atlanta 585. So Chicago to Atlanta 585, and then we have Dallas 803. That's Chicago to Dallas 803. Okay, as to where you are going to put the vertices here, you can actually pattern it from the actual location of the cities in the map of the United States, or you can actually put it anywhere as long as the connections are of the same. Okay, so it's actually, you learn that it's actually how they are related or connected to each other that really matters in graph theory. So one of the Hamiltonian path is Hamiltonian, referring to, okay, don't forget that we need to visit each city exactly once. You may use any route, available route, or available edge, but you need to actually just visit the city exactly once. So the one example of a Hamiltonian circuit is from Chicago to New York. So we have Chicago to New York to Dallas, and then we have to Philadelphia, and then we go to Atlanta, and then you go to Washington, and then you go back to Chicago. So as you can see, we just visited the cities exactly once. We do not repeat. And then there's a total weight. So you have to count. You have to actually sum it up. So we have Chicago to New York, that's 713. Then you add that from New York to Dallas, it's 1,374. Okay, and then the other one is Dallas to Philadelphia, that's 1,299. And then you add again, we have at Philadelphia to actually Atlanta. Okay, so that's 670. Then Atlanta to Washington, that's 544. This line here. And then the last one is Washington going back to Chicago, 597. So you need to get the total of that, and that's the total weight. And then the question here is this the shortest path, or is this the one with the minimum weight? So it's a matter of what we call, it's a problem on traveling salesman problem, looking into the optimum solution, a solution that gives us the minimum cost, the minimum time of travel, the minimum distance, if these weights are referring to those, if it's a weight, or I'm sorry, if it's a time, it's a distance, or a cost of transportation. So we're looking into the minimum, the minimum weight, total weight. So that's one possible circuit. Okay, that's one possible circuit. Okay, you can actually take another circuit here, another path or circuit, Hamiltonian circuit, visiting all the 6 cities. Okay, and then that will be your assignment. You need to make more, or you have to find other circuit here, which is actually the total weight is actually less than this. So find the minimum, find the lowest. Okay. So there's one algorithm on how to find the minimum weight. Okay, so this is just one pattern or one technique on how to find the minimum weight. Okay, we call it the greedy algorithm. So first, you need to actually choose a vertex to start at, or in some problem, it's indicated where you are going to start. Then travel along the connected edge that has the smallest weight. So you need to choose the edge with the smallest weight. After arriving at the next vertex, travel along the edge of smallest weight that connects to a vertex not yet visited. Continue this process until you have visited all vertices. And you need to return to the starting vertex. And that becomes Hamiltonian circuit. Okay, let's apply the greedy algorithm in this certain graph here. So using the greedy algorithm to find a Hamiltonian circuit, okay, and starting at vertex A, so it says here, you start at A, then you compare which is the lowest. We have here A connected to F13, A connected to E5, A connected to D is 4, A connected to 15 is C, to C is 15, I'm sorry, and then A connected to B is 8. So the lowest is 4, so we need to connect it to D. Okay, and then looking into the lines connecting to D, the lowest is 2 here 2. We have 12 here, we have 8, we have 7 here, and 2 is the lowest, so we go to B. And comparing also the lines connected to B, we have 8, 5, 11, 6. So we have 5 here. So we need to go to F. And then also, we did not yet visit C and E. So comparing the weight, 10 and 14. So we need to visit letter E. Okay. And then since C is not yet visited, that's the last one to be visited. So you need to actually visit that. So we visit C, and then you need to go back to A. And you take this route here, or this line here. And that's actually an Hamiltonian circuit. And the total weight is 42. Okay, and then you can actually find another circuit and check whether that's greater than or maybe less than 42. And if it's less than 42, that's the solution. That's what we call the optimal solution. Because in here, we need to minimize the cost, minimize the time to travel, and the distance. We're looking into the shortest path. Okay. And then this one is another graph, and you may try it using the same algorithm. So I will give you this one as an assignment. Please try to answer this using greedy algorithm and check whether you get the lowest or the minimum weight. Same with that of the problem a while ago. So this one is also Asian cities. A while ago are cities in the United States. In here we have cities in Asia. Okay, so you should know, okay, how to connect, okay, all these cities through these vertices here. I'm sorry, these numbers here. Okay, these are airfares, okay, going from one city to another. So you can actually arrange the cities based from the actual location in a map here. You can arrange them like that, and that corresponds to the vertices. 1, 2, 3, 4, 5. So there will be 5 vertices. This is actually Tokyo here. This is actually Seoul. Okay, and then we have here Hong Kong, and then you have Beijing, China here in Beijing, and then we have Bangkok here, Bangkok. So that can be the arrangement, okay, but it's not actually compulsory that you have the same arrangement with the actual location of these cities. And then since everybody is connected to itself as to its cities, because there's an what do you call this, a route from one city to all other cities. Okay, so there will be a line. Let's say for example for Tokyo, Tokyo going to Hong Kong 8:45. So to, Tokyo to Hong Kong, so you put 8:45 here, and then Tokyo to Bangkok. Okay, so there's a line here, and airfare is 1,275. So that's the weight, and then we have Tokyo to Seoul 470. So where's that? Yeah, that one 470. And then you have Beijing 880. So you have that. And you do that also for the next row here for Hong Kong. So Hong Kong to the Tokyo. Okay, so same. That's the same with that. We're done with it. 8:45. That's it. So the same. Then we have Hong Kong to Bangkok. So Hong Kong to Bangkok here. There's a line, and then that's 320. So you need to finish all of those, and that's actually the graph. And check whether there will be Hamiltonian circuit. Okay, so you use the greedy algorithm. Okay, so for this video, that's all. We will learn more on this topic in the next video. Thank you. Bye.